deals with fundamental entities of physics. Particles like photons, electrons, neutrons, from which matter really built, photons that carry electromagnetic radiation, various elementary particles that mediate other interactions in physics. Usually we call them particles in spite of the fact that some of their properties are totally unlike the properties of what we call particles in our ordinary classical world. For example, a particle can go through two places at the same time and can interact with itself. This cannot happen in classical world, but it could happen in quantum world. Because of that, quantum physics is fully counterintuitive, mysterious, and even paradoxically vague. Next slide. Next slide. No, no.
Sorry?
Skip করে আগেরটা আগে আগে আরো আগে
Okay, okay,
আরো আগে
okay.
আরো আগে
আরো আগে আরো আগে
আরো আগে
Return.
না 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 আরো আগে আপনি স্কিপ করে চলে যাচ্ছেন প্রথম দিকে ছিল আরো আগে
আচ্ছা ঠিক আছে
পিছনে পিছনে যান পিছনে যান তারপরে যান পরেরটা যান আবার বেরিয়ে গেলেন হ্যাঁ ইনফরমেশন এর পরের পেজটাই যান এর পরের পেজটাই
পেজ ডাউন কর চলি হলো
হচ্ছে না মাউসটা কাজ করছে না
ও বাবা
এক মিনিট দাঁড়ান মাউসটা কাজ
স্যার
করছে
একটু ওয়েট করুন এবার
ঠিক আছে
ওকে
Now next subject, information theory.
ওকে
This is a subject of communication theory. What is the objective of this subject? To send or process information or data to distant locations or laboratories, whatever you can say, through some communication mediums. These communication mediums are generally called channels. How reliably? This what should be careful. This communication should be reliable. Practically, reliable transmission is really difficult to achieve. Many factors are responsible for sending different messages. Skip করে গেছেন আপনি পরেরটা হ্যাঁ messages to many places in undisturbed way. আবার স্কিপ করে গেলেন তো আপনি আমি বললে আপনি যাবেন হ্যাঁ therefore the subject is challenging in both ways, the theoretical development as well as its implementation. Next slide. Computer science, a subject everyone knows that generates enormous speed in computation. What a high level computer could do? A high level computer has the ability of computing difficult calculation in such a short time that is really impossible to achieve with a few number of human beings. Human beings can do that, but not with this short schedule, within a finite schedule. The basic ingredient, what is the basic ingredient for this capability? It is nothing but the parallel processing. This is known as parallel processing. Okay, next slide. Next slide. Now, I am no, আগের স্লাইডেই যান the two branches of science, physics and mathematics, are not merely the subjects that are used to solve some difficult problems. I want to give some comment because this is very important. They have enormous impact in developing an outlook of our everyday life. It is actually the scientific way of thinking. The logic is simple, elegant and natural. This is the fundamental objective of basic science, whatever we are doing now. Okay, next slide. What is quantum information theory? To solve basic tasks of information processing using quantum mechanical principles. What does it mean? What actually usual information theory did? Usual information theory is governed by the laws of classical physics. Which are those laws? Like Newton's laws of motion, etc. along with usual laws of probability theory due to Kolmogorov and others. In information theory, those who have acquainted with this subject know that probability theory is a very fundamental thing to understand information theory very clearly. And this is generated by Kolmogorov and others. Now, next slide. Next slide. However, the governing laws of quantum theory are different to that of classical theory. Here, there is no principal law. We need an axiomatic way to develop this subject. What is the logic? The logic is actually known as quantum logic, but it is very much counterintuitive. It is not proper sense we could say. There is a structure called orthomodular structure for mathematicians. This kind of structure is needed to describe quantum logic. Almost all the inventions of quantum mechanics are counterintuitive in nature. It started with the behavior of systems in small dimension initially, like theory of relativity started with the behavior in high speeds. Next slide. Okay. So this is the introductory part. I have said what are the basic status of the three subjects: quantum mechanics, information theory, computer science, and just what is quantum information theory. Just I have given some definition, nothing else. Now I will show 4 examples. By that you can understand what is the power of this subject actually. There are 4 examples I have put. Okay. First one is a BB84 cryptographic protocol. Next one is a algorithm, Joyce algorithm. Third one, quantum teleportation, and last one, if I will spend only little on dense coding, super dense coding. Now, for the first thing, BB84 protocol, our country is actually here. This protocol comes in a Bangalore conference in 1984. One of the greatest scientists in this subject area, Charlie Bennett, is one of the author of this paper, and this is a very important thing I will explain. Okay, next slide. Next slide. Now, what are the responsible quantum factors for all such examples? I will explain. One thing is the existence of non-orthogonal states. Non-orthogonal states, if you have a inner product structure, then if they have inner product non-zero, then they are non-orthogonal. States are also mathematical properties. In that sense, they are non-orthogonal. In other words, this non-orthogonality means some physical meaning. There exist states of a system that are not perfectly distinguishable. And next one is the quantum entanglement. This is a kind of quantum correlation and a resource like energy. This is most important word in quantum information theory, quantum entanglement. Actually, my research area is to understanding of quantum entanglement basically. It exists when there are more than 2 systems, because for correlation you need at least 2 systems. The behavior of composite systems are not always predictable. Okay, next slide. Now I am explaining BB84 protocol. What is this area of this subject? The area is the cryptography. Everyone knows that Julius Caesar sends messages to his army in some cryptic language. Also, you find in the story of Sherlock Holmes, there are some dancing figures like that, and these are nothing but some message which is actually written in a cryptic way. So cryptography is a very old thing. In defense and security things, cryptography has very important impact. And for the understanding of this, mathematicians have very big role. Basically, algebra is the core subject for explaining cryptography. Now, what is basic task? To share a secure key. Why? Answer is that to send secret message. We have to send some secret message from some sender to some receiver. Now, in classical cryptography, in principle, there is no perfectly secure classical cryptography. There is, in principle, you should understand that in principle, there is no perfectly secure classical cryptography protocol. Maybe time require much, but one can actually, with some time, can break this cryptography. However, in this BBIT protocol, the achievement is no eavesdropper. Eavesdropper means third party who want to learn the message. No eavesdropper will be able to extract any information without being detected. But actually, here I am explaining what actually happens. Some sender sends some secret message to some receiver in a distant location. And there are intermediate, many people or machines, whatever may be, they are trying to code this message. They want to learn this message. But their attempt will be successful only when they are not detected. If they will be detected, this key will be rejected. The sender and receiver will reject the key, what they are sharing. So the third party's attempt will be that they will not be quoted by the sender and receiver. That is the success of third party, and by that way they can actually learn what sender is trying to send some secret message to receiver. You know that in defense or something else, if that happens, then it is a very big threat. So sender receiver both will not wanted to disclose its secrets. Quantum theory guaranteed that. Quantum theory actually guaranteed that a eavesdropper, if tried, he or she could succeed for a while, but for some time they will be caught. Then what sender receiver, they will generate a new key. So this is very good achievement as far as qualitative is concerned. Now next slide. I will explain little bit about the protocol in short. So there are three persons, Alice, Bob. Alice wants to send secret message to Bob, and Eve is the third party who wants to learn their message. Now, in the language of bits 0, 1, Alice creates a random bits 0 or 1, and there are some operations I just said, don't bother about this. These are some operators, Z basis, Pauli Z basis, encodes this data. You should only cope with this, that there are some mathematical things which have some physics is going on. Okay, you just understand only these things and the result. Encode is data bit either in Z basis or X basis, and then sends each qubit by a quantum channel. After receiving, Bob measures his qubit in Z or X basis at random. Next slide. Next slide. Alice broadcasts her choices of basis sent, and Bob also broadcasts his measured basis and then check their result. if there is any third party, if more than an acceptable number disagree. Actually, if tried to know that, then their result will not agree at all many times. And then they abort the protocol. Started again with possibly a different quantum channel. Sometimes Eve may succeed, but on a long run, she would be detected. And success rate is very success rate of Eve, not sender receiver. Okay. Now this BB80 protocol generated through non-orthogonal states by photon polarization by Bennett and Prasad in 1984. Later in 1991, Arthur Rickert, he is a British scientist, he transferred this protocol using another word I have said, quantum entanglement. So, what is the basic key ingredient from this BB84 protocol? There is a secure cryptographic protocol exists in nature. What I have said for the classical cryptography, in principle there is no perfectly secure protocol. Here, quantum mechanics guarantees we have a perfectly secure protocol. This is qualitative difference between quantum and classical world in the cryptography. Okay, next slide. Now, next thing is that an algorithm. This is another important achievement. Firstly, David Dwyer invented this, then Joshua joined this, and their composite algorithm is known as Dwyer-Joshua algorithm. And for this protocol, David Dwyer and Joshua both are given Sir title in England. This is a very prestigious title. Now, what is the basic task? This is a very simple mathematical task. To find a Boolean function means two-valued function, 0 or 1, say, whether balanced or not. What does it mean? Balanced means half of the time it will take 0, half of the time it will take 1. Okay. Then we call that function, Boolean function, is balanced. And constant. Constant means all the times it will take 0 or all the times it will take 1. Okay. So we have the basic task whether a Boolean function is balanced or not. So what is the usual computation complexity? This is a very solvable problem, not a difficult problem at all. Usual complexity with the order of string length. How length or a vector of size n or n plus 1 or something else you will take. With this length, string length is the usual computational complexity. What does it mean, this computational complexity? How many number of operations we need to succeed this algorithm? This number will give you the complexity of that algorithm. Every computer algorithm has some complexity, and there are many complexity classes, etc. when quantum mechanics came into play. Now, I am not going to that things. Now, usual complexity is the order of string length. Now, what is the advantage of this Dwyer-Joshua algorithm? Here we require only one evolution by an unitary operator. You know unitary matrix, unitary operators, followed by a measurement. Only one operation here we require, an unitary operator followed by a measurement, by which a red light or a green light will illuminate, and by which by red light we say the function is balanced, or by green light we will say that function is constant. So there is no computational complexity at all in this protocol. This is the important thing in Joyce-Josa algorithm. And not only that, the algorithm always succeeds. But for that, we require quantum gate. There are some logical gates. Many may know that AND gate, NOR gate, OR gate, XOR gate. Many gates are there. These are all classical gates. But in quantum theory, for this kind of achievement, we need quantum gate. And in classical gates are not all reversible, but in quantum gates, as they are unitary operation, so unitary matrix has inverse. So all the quantum gates are always reversible. Next slide. Now I am giving the algorithm instance. What is the promise? The function is that x from 0, 1 to the power n to 0, 1. So string length is here n. We have to find it is either constant or balanced. In worst case, classically we require 2 to the power n minus 1 plus 1. So it depends upon n, number of evolution. Now, what is in this Joyce-Josa algorithm? We have to take some quantum state. And a typical type of Hadamard transformation, this is something superposition kind of things that we have to achieve. Next slide. The function f implemented as a quantum oracle, the oracle maps a product state xy to xy plus fx. This don't bother about this because this language is modern quantum mechanical language. Then the quantum oracle gives something like that. I am not explaining because many one don't understand this kind of symbols. Check of the two possibilities for fx and ignore the last qubit and apply a Hadamard transform to each qubit to obtain that. Okay, next slide. Now there is after a probability you can check which evaluates 1. You can check that if someone have any interest, they can go to this paper. And if fx is constant and 0 if fx is balanced. The circuit diagram is like this. Okay. Next slide. Now I am going to the most important invention in quantum information theory. Actually, after the invention of quantum teleportation, this subject generates quantum information and now one of the most successful invention of quantum information theory. What is the basic task? Here the basic task is we have to send unknown information to distant location. What is the, one can say, what is the big deal about it? I am explaining that. There is a no cloning theorem, famous. You know, in biological science, there is a very big achievement in 1980s and 78, 80s like that. Dolly is something generated as a copy of a pig. Now, in biological science, you can replicate some cells. So replicate means you have clone copy. So in biology, and it has very good impact in modern medical science that we could actually, by cloning, we could actually generate in many places, some says, etc. It's possible. But what about in physics? In 1982, next slide, okay. In 1982, to get scientists, Wouters and Jurek, they have published a paper in Nature which says that cloning is not possible. What does it mean? I'm explaining in short. Think about a Xerox machine. What is its objective? It is to copy the matter printed in a paper to a blank page. This is the method. Sometimes we call these are copier machines because it can do copy. Quantum cloning machine, if exists, acts like a Xerox machine but copies the information encoded in physical state. This we need a copier machine for copying physical state, information encoded in a physical state. But Wouters-Jurek result in 1982 that is published in Nature said that cloning is not possible. This is called no cloning theorem, which shows our incapability of copying unknown information. So unknown information you cannot copy. That is an important message found in 1982. Next slide. Now, then people are thinking if unknown information is not copied, is it possible to send unknown information to a distant location? I am giving an example. Suppose I want to send some secret information to my friend at America. Okay. Now, I do not want this information could be disclosed anywhere. But there is no way I have to take some help of some agencies. But if there exists an agency which could send my information without knowing anything, then it's okay. No problem at all. Here, the business is like that. In between some agency, they do not know what is going on. But sender and receiver knows that sender sends the secret message to the receiver. They both know that receiver knows that he actually finds the secret message. In between the agency, they do not know what was the message was. Okay. Now I am explaining again little bit. Suppose there is a sender A and there is a receiver B. They are far apart in say two different countries, even in different planet also. In between them, we must require some channel. This is known as quantum channels. Otherwise, this protocol will not succeed. An unknown qubit or information, qubit means quantum bit, information is given to A. After the whole operation, the particle of B is prepared in the unknown state. What is? There is a particle in the hand of A that is prepared in an unknown state, and after the whole operation, this particle will be transferred in this unknown state. Or the state of the particle of A will be lost. A could not be try to learn the information at all. That is, it is possible to send unknown information to distant location. How much resource you require? For this quantum channel, you require some entanglement. There is a measure of entanglement called 1-bit entanglement. And you also need some classical communication by telephone or telegraph or something else. And for that, you need 4 different messages you have to need. So 2 classical bit of classical information, classical communication you need. Okay. Next slide. What is the interesting feature? Both A and B do not know the actual information encoded in the qubit. Shared entanglement is lost in the process because it requires that thing. Entanglement here used to achieve this protocol. If you do not use entanglement, then this protocol will not be successful. However, this would not help one to transmit information supernominal. There is nothing supernominal communication or like that. Nothing else. This is a very peaceful coexistence between special theory of relativity and quantum mechanics. So, also in quantum coding, we find some very interesting coexistence between theory of relativity and quantum mechanics itself. There are very good results. We have also some result on that. Next slide. Now, I am giving some mathematical as well as physical flavor. The joint state like this is psi 1, 2, 3. Psi 1 is the unknown state, and 0, 0, 1, this is the channel state. Psi 1 unknown means this A and B, A0 plus B1, this is a superposition of states. This A, B are unknown. Alice does some measurement called Bell measurement. There are 4 outcomes possible. The measurement result then communicated to Bob. According to the measurement result, Bob applies 4 unitary operations in his place. The state of that third particle, that is Bob particle, is then prepared in the state side. There is a involved mathematics in that. I am not going to because all I have to use Dirac notation, etc. Okay, next slide. Okay, previous slide. You go to the previous slide. So that means that one can actually achieve that unknown information could be sent. And after this achievement by, there are 6 scientists involved. Bennett, one of them, Bennett, Brassard, and there are Utars also there, Smolin there. There are 6 scientists involved there. After this achievement of quantum teleportation, quantum information theory actually generated very quickly. People thinking there are something happens in a new way. Not only that, how to use this entanglement in different perspectives that has been evolved. And for the last 25 years to 30 years, enormous research has been done. Enormous. Each and every day, there are a lot of papers published in this field. there is a archive called quantum physics. You find there are a lot of things where some theoretical as well as experimental, lot of things. And not only that, this quantum teleportation is experimentally done by many people in the throughout the world. This is actually experimentally verified, this protocol. It is not the theoretical things. It is already experimentally verified by many groups throughout the world. Now, next thing is that just next slide is the next slide is the dense coding. It is just the opposite to that quantum teleportation. Here, basic tasks send classical information using entanglement. It is also true, possible, quite reverse than that of teleportation. Here, both sender and receiver share a prior entanglement. Sender does 4 unitary operations on his part to send 2 classical bits, say 0, 1, 1, 0, 0, 0, etc. and receiver delma. Actually, this dense coding is invented in 1992. But after the invent of quantum teleportation, people learn that this dense coding is also very important thing. Because this requires complexity lower than usual complexity. Usually we require 2 classical qubits. But using quantum mechanics, only sending 1 qubit this achieves. So there is a big power of quantum theory. All these 4 examples shows how much powerful the quantum theory is for generating this new subject, quantum information and computation. I am explaining these 4 in short. Possibly everyone could learn that. Next slide. Now some of the observations you find very important. What are the observations? Quantum information theory shows its power by using basic principles of quantum mechanics. Entanglement and existence of non-orthogonal states are the key features of these achievements. Entanglement here used is like energy in classical physics. In quantum information theory, entanglement is like energy in classical physics. And there is a very powerful underlying mathematics. I will explain later on what is the underlying mathematics I call. Next slide. Now, theoretically, there are lots of results discovered within the last 20 years. However, the question is now of implementation of above results. Already there are some major achievements in the experience. Many people are now working in the field of implementation. One of the most important tasks, how to build quantum computer. Are there sufficient technology to implement? Here I will devote something that in India is also in this run of building quantum computer and etc. Government of India has taken a national mission on quantum technology, NMQTA. In China, they have devoted very large amount in satellite communication. They have actually going far more. Not only that, for quantum computer, you know these 2 companies, one is IBM, another one is Google. They have some word like this, and one recent result says Google supremacy. These are all going to the building of quantum computer. When quantum computer will come, then this kind of laptops, etc., they are simply outdated. You cannot imagine how fast those machines will be. This quantum technology, if properly built, then it will give enormous power to human nature. We have been a very important technological era. We are going to this field. We don't know actually what is going on. Now all are in the realm of now research. Physical things is not come out till now. Not only that, uh, in Geneva there are some group, they have tried very good experiment also. And if in future there are lot of things to invent also. Next slide. I'll give some other comments also. Put forward. Actually, there are several aspects one could find interesting to devote himself or herself in this field of research, especially apart from background of physics. Mathematicians throughout the world did a lot. There are many good mathematicians are devoting in this field of quantum information computation. I am explaining some of these. Firstly, the basic mathematical structure we require to describe quantum theory is nothing but Hilbert space structure. This we minimally require, Hilbert space structure. Next slide. Next, as a simple mathematical problem, one can think of characterization of positive operators on such Hilbert spaces. Now, positive operators means as a mathematics student or teacher also, you think of a positive matrix, that means which have eigenvalues non-negative. Okay. But this specific kind of operators has many nice features. Through quantum theory, this quantum information theory, many things evolved. Their characterization is not complete yet. There are unsolved problems. A class of such positive operators known as physical operation also. They have nice characterization. They are called completely positive maps. But there is a very big question. Given a positive map, is it completely positive or not? The question is not easy to answer at all. Giving you a positive matrix, you could not say that this positive matrix is a completely positive matrix. There are some characterization, I am not going to these things. Next slide. Rather, a related question one could ask. If a map is not completely positive, is it then useless? So there are two questions. One question, whether the map is completely positive or not. Another one is, if it is not a completely positive, then it is a useless operator or not. If the operator is not completely positive, then it is not useless. They are also important in quantum information theory. They can actually use to identify different kind of entangled states. So here there is a very important mathematical theorem involved, Hahn-Banach separation theorem or extension type theorem. These are used in those results. So characterizing positive operators is a very important. So positive operators on Hilbert space, they have very important implication. One thing I said, that composite physical system, we need a many Hilbert spaces, and for that we need some other kind of operation. These are called tensor product. So tensor product of Hilbert spaces is the basic structure of a composite physical system. Composite physical system means there are lot of particles, etc. So tensor product structure we need to understand also very well. Otherwise we could not do anything theoretically in this field of research. Tensor product structure. So from the viewpoint of mathematics, this field is a very open and wide. Don't need to understand the physics itself. You can devote only the mathematical part. Some other quantum physicists will implement that result. But if you find a important result in this field as a mathematical result, that has enormous impact in physical theory. Another important aspect of study is complexity theory. This field actually dominated by mathematicians. Complexity theory totally dominated by mathematicians. Only few physicists you could find. This, and there are so many, over 400, 500, or now maybe around 1,000 complexity classes generated through this quantum theory. So mathematician has many things to do. Apart from other people from other fields, physics itself, chemistry, electronic science, computer science, and many other, electrical engineer, many from many disciplines you can enter in this field. Actually, throughout the world, there are many people are devoting in this field. Next slide. Now, there are several unsolved problems as well as conjectures where mathematicians could enlighten us. I am also giving you this flavor that there are actually in this field of research, there are several unsolved problems and conjectures. If you search in Google, you find a list of how many unsolved problems there are some conjectures where mathematicians could enlighten. However, those results could have far-reaching consequences in physics. For example, understanding the nature of quantum correlation is related with the famous correlation conjecture. So many things happens in this field of research from the point of view of mathematician, from the point of view of physics, from the point of view of computer scientists. There are a lot of things to do. I am completing my lecture here. Thank you all. Next slide, please. Any question?
Thank you very much, sir. Thank you very much, sir, for your nice deliberation. You have presented a complicated subject in a lucid and fascinating manner and enriched us immensely. I am sure that the audience has also enjoyed it. Our colleagues and students are eager to hear more from you and have put forward some questions related to this subject. So let us move on to the question and answer session. Professor Deepa Chakraborty, an associate professor of the Department of Mathematics, will coordinate the question and answer session. Professor Debobroto Mondol, an assistant professor of this department, will assist her in this session. Over to Professor Chakraborty.
Hello.
Deepadi?
Hello.
Okay.
Hello, Professor Devashish Sarkar. Thanks once again for delivering such a nice talk and introducing us to quantum information science. I sincerely hope that this webinar on this interdisciplinary topic will motivate the participants from diverse backgrounds. Now we start our question answer session. I like to inform that at the time of registration, we find some questions from participants, and those are already sent to the speaker, and it is sure that almost questions are covered in his lecture. Now, I will like to share the questions from the live chat box with the speaker accordingly, and from YouTube also. Okay. First question from our chat box. Any linear algebraic point of view is there with cryptographic feature in area of computer quantum computation, and how to solve traveling salesman problem using quantum computing?
This is a NP hard problem, this traveling salesman.
আমারও তাই মনে হচ্ছে।
So that's in the complexity classes. So quantum algorithm can solve everything that I could not say.
সেটাই, মানে এটা তো একটা বিশাল
linear algebra is very much involved in this subject, because this what I have said, Hilbert space, etc., everything is that linear algebra.
Yes.
So the structure is linear algebra. You require very good in linear algebra itself. If you learn matrix theory very well, then you know. One of the very great mathematician, Van Paulsen, I have personally know him. We spent 1 month at Paris at Van and myself. He's also sometimes in India also. He's a very great mathematician. He is doing in some conjecture level things. He said only one thing: if you understand matrix theory very well, then you will cope with this subject.
Yeah.
So learn matrix theory very well. Then tensor
second one,
everything you could learn very well. So linear algebra is important thing we have to learn as a subject. Next thing.
Second one, in any interdisciplinary problem can be solved as an example.
Yes.
In any interdisciplinary problem can be solved as an example.
Quantum information computation cannot resolve every problem, but they can address many problems which earlier are not possible. But that does not mean that quantum information theory will resolve all the problems. It has some shortcomings also. What I have said, that quantum correlation, this nature has also some shortcomings or many things. You cannot do anything. Giving quantum means everything is possible. That is very big misnomer. So one can try with this new theory. If succeed, then it's a great achievement. But it can be a failure also. So no, don't worry about this. That is a again some put forward, because with this theory this is not possible. Then they can say that is also a good result for a
Good
problem.
result.
If someone said with this theory this is not solvable, that is also very important.
Another one, um, why is required the quantum computation and how is performed?
What? Again?
Why is required quantum computation and how is performed?
Quantum computation is required for solving difficult some problems which is not possible, and for that we need quantum logic gates, quantum computer, etc., new kind of devices by which you can do these quantum computation things. And people are thinking this, and what I have said, this speed of this quantum computer will be just out from every computer what we are now using, even if supercomputer,
Mhm.
because a qubit can store uh, more powerful than usual thing. So qubit is a very important thing, and the information is stored in a qubit.
Really?
Uh,
Code
so we require subatomic level particles uh, things in this quantum computer.
okay. Correlationship with pure mathematics. Correlationship with pure mathematics.
Yes, I have said that already. I have said that there are some problems which you just take as a pure mathematical problem. Hilbert
Right.
space and operators.
Uh,
Then you will find many results. Don't
many
worry about what is the physics itself. And in complexity theory, everything is pure mathematics. There is no quantum, nothing else. Everything though, and what I have said, that there are a lot of mathematicians are working on this, and these are all pure mathematics. Forget about quantum.
forget.
Just take a problem. This is Hilbert space, and there are some
And
operators, etc., etc.
all other questions are in your lecture.
Mhm.
Uh, Thanks a lot once again to Dr. Sarkar for addressing all questions from the participants. Now we hand over the stage to Dr. Krishnanko Shekhar Gayan, an assistant professor of our college in chemistry department and also a member of IQAC on behalf of IQAC. On behalf of IQAC to give the vote of thanks and uh, ending session.
Unmute.
Unmute karo. Krishnanko.
Thank you. On behalf of Internal Quality Assurance Cell of Raja Peary Mohan College, I would like to convey my gratitude to our speaker, Dr. Debashish Sarkar. His lecture on an introduction to quantum information and quantum computation was very informative. There is a well-known saying by Niels Bohr that those who are not shocked when they first come across quantum theory cannot possibly have understood it. Now we all know the language of quantum theory lies in mathematics, and he has tried to explain through his lecture today. I hope this lecture will benefit not only our UG students, but all others who are engaged in this field of study. Thank you very much, sir. Next, I would like to thank all the participants present today, as well as our principal, sir, and to our Microsoft support team for their cooperation. Thank you, everyone. Have a nice evening.
Thank you.
Thank you.
Thank you.
I am leaving. Okay.
Okay, sir.
Thank you.